Okay, hello everyone, and welcome to the Center for Econometrics and Business Analytics seminar series. Today we are having Joakim Westerlund from Deakin and Lund universities, and with his talk about interactive effects, panel data models with general factors and regressors. Joakim, do you want the questions during the talk or at the end?
Please interrupt me. So if you have something, just shout out.
Okay, thank you.
Immediately. All right. Thanks, Anton. Thank you for inviting me here. I would obviously, it would be really nice to meet you guys in person, but this is also extremely efficient. So I've already been at work. I've been at the gym. And now I'm back home, and now I'm having a seminar in St. Petersburg. So pretty full-on day. Yeah. So thank you very much for having me over. I looked at the members of the center, and I saw that people have kind of diverse backgrounds. So I'll go into a little bit of motivation in case people are not familiar with this topic. And so I will explain most of these things in the title in a little bit. But it's about panel data, linear panel data regression model with certain forms of unobserved heterogeneity that we want to control for, while also allowing very general heterogeneity and general regressors. So it will be a general form of a linear panel data regression model. Such models are in economics. This is the workhorse of the applied literature, I would say. So this is partly the reason for looked at this. And so this is joint work with Bin, Liang Yun, and Yon Rong. So Bin and I were colleagues at one point at Deakin in Australia. Now he has moved on to Monash, also in Melbourne, Australia. But this project started there together with him, and then it expanded a little bit. In this paper, so there are many reasons, of course, for wanting to look at panel data. One is increased rates of convergence. Typically, if you assume that coefficients are homogeneous in a certain in one of the directions of the panel. The other one is that you can control for unobserved heterogeneity factors that might potentially be correlated with regressors, and that would otherwise cause inconsistency. So this we can control for in the panel data setup, and this is the main reason for why we look at it here. And the most common approach by far, and this is the workhorse for sure. This is the effects specification, and so then in the linear regression case, it will look something like this. So you have your dependent variable YIT. So I is here the cross-section index. So these could be firms, individuals, countries, whatever. T is the time dimension. And here we have a observed component, x prime beta, and then we have an unobserved component. So alpha, theta, and epsilon are all part of the error term, and this alpha and theta, these are unobserved effects that could potentially be correlated with x. We don't know them, and so had you had cross-section data or just time series data, you would have to have observations on these. Otherwise, least squares estimator of beta would be inconsistent. But here we don't really need observations on these, but we can control for them anyways by simply demeaning the data. And in this in panels, these fixed effects typically they are super important. So depending a little bit on the context, but if one takes a in macro and finance, these are typically super important. And regressors not always explain a whole lot of the variation in Y, but the fixed effects does. So there's an example there by a paper in Journal of Finance, I think, on leverage model for firm leverage. There, the fixed effects accounted for 90% of the variation in the dependent variable. So typically this is important. So I'm bringing it up here as an indication of the importance of controlling for these things. The problem is then obviously that these fixed effects, they are not always enough to control for this unobserved heterogeneity. So the idea is to control for missing regressors, omitted variables that would otherwise create bias in inconsistency. And so whenever tested, this hypothesis that the unobserved heterogeneity is made up of these fixed effects, this is typically rejected. And so one would like to have something that is a bit more general. And so this is what we're working on at the moment. So this is the state of the art, one might say. It's an interactive effects specification. So it's the same linear regression model before, in that the model is linear in the regressors, but this unobserved heterogeneity is now it has this multiplicative form instead of the additive form that we saw before. And this is more general than fixed effects. You can see it by just in gamma is alpha 1 and F is 1 theta, and then you simply do the multiplication, and then you see that the product here becomes indeed alpha plus theta. So fixed effects is just a special case of interactive effects, and this can be important. So if you imagine Y being I don't know, inflation or something like this across countries, then one potential candidate for a common factor could be business cycle effects that are felt for all countries in a panel, but then obviously not all countries react in the same way to the business cycle. Some are affected in larger extent than others. And so you would like to allow for country-specific loadings or effects of this common factor. And so therefore it makes sense to have this multiplicative form where gamma is here, this loading is allowed to vary across countries, and F is the common factor. So here, this business cycle. And so this is where we are model-wise. To estimate this type of model, there are more approaches. I'll focus on these. So there's also, one can use GMM as well. But the two most common approaches is the common correlated effects approach. This was proposed in an Econometrics paper by Hashem Peseran in 2006, and there is a principal components-based approach that Yushan Bai proposed also in Econometrics 2009. These are the two most common approaches. So basically here, what you do is that you estimate the factors in the first step. So you estimate F in the model that we had, and then you simply replace true F by this estimated effect. So you regress Y on X and this estimated factor. So you condition out the effect of this unobserved heterogeneity in this way. So this CCE approach, this has some benefits to it. So above all, it's super simple. And so therefore it's also very popular in the applied literature. But it has some drawbacks as well. Obviously, there's a cost to this simplicity. And some of these costs is that it requires that the regressors have a linear factor structure. So the factors f that were in the equation for y, they should also be in the equation for x. So this can be restrictive. So if you think about models, not totally uncommon models where regressors enters in squares, for example, or legs or something like this, then this assumption is violated. So it's obviously better if you don't need this assumption. And another assumption is that the number of factors is bounded by the number of observables. So if you have a certain number of regressors plus your y variable, then that number is a top upper limit on the number of factors that you can allow. So this is not the case when you use this principal components approach. And so for this reason, most of the literature focuses on this principal components approach. Although in applied literature, as I said, CCE is very, very popular. But we will, for these reasons, we will focus on PC in this paper. And as I said, there are other approaches, but these are, I would say, these are the most common ones. Just briefly about the contribution of the paper. So the overall contribution, it has kind of like two sides. So one is empirical, the other one is theoretical. So the empirical one is that, so the empirical contribution or appeal of the paper is that the factors and the regressors, so f and x in this notation that we had, they're essentially unrestricted. I'll go into the details soon, but there are little or no restrictions on those. And this, we can allow this without really having to know anything about how the data generating process looks like. So this is something that we will estimate with the other parameters of the model. So this is something that we will figure out along the way. A little bit more about how these factors and regressors are generated. I'll come back to this. Basically, since the factors are essentially unrestricted, there is no need. So the factors, you can think of deterministic components, so constant and trend, for example, that you might like to have in the model. This is nothing that you need to decide on beforehand. So since f is unrestricted, you can treat also deterministic components as a part of the unobserved heterogeneity, and you estimate this from the data. So you can treat this uncertainty, if you will, in practice over which deterministic components to add. This then becomes a part of this general estimation problem of estimating f. Also, since x is basically unrestricted, there is no need to test for unit roots and such that is otherwise quite common in the literature. So this is good because then there is no pre-testing bias from testing the regressors. So this is also nice, I would say. The main requirement is that on the factors and regressors is that we will assume that certain the second moment matrices of these factors and regressors, they satisfy certain conditions, and that they have well-defined limits. I'll come back to this, but this is, as I said, it's not very restrictive and holds in most models of that you could imagine. If you compare to the existing literature, so compared to BI, for example, which is this paper that I mentioned before, he assumes regressors and factors to be completely stationary, and most of the literature does. There are some exceptions, but they instead assumes that either factors or regressors or both, that they are pure unit root processes. And this too, of course, can be restricted. So it would be better than to have an approach that do not require these restrictions. So this would be then the main empirical contribution of the paper. The second contribution is the theoretical one. In terms of theory, as I said, so the literature that exists either assume factors and regressors to be stationary or unit root non-stationary. And so they haven't really considered any other specifications. And so this is the main theoretical contribution to step outside this pure stationary, pure unit root environment. The main difficulty from a theoretical point of view is the fact that the regressors are unrestricted is not that problematic. The main problem is that the factors have such a general specification. So the main difficulty here is to control somehow for the fact that the factors may have different order of magnitude. So I'll come back to this, but you can think about this at this point as different degree of trending or different degree of integration if they are stochastic. So think about it in those terms. so this is the main difficulty, and the reason, basic reason, is that when you estimate the factors using principal components, then principal components is a nonlinear estimator that tends to distort the signal coming from the factors if they have different order of magnitude, and this is something that we deal with in the paper. And the solution then is basically to do what Yushin Bai did, but you do it in an iterative fashion. And I'll come back to this exactly what this is. So these are the contributions. So first, from an empirical point of view, you can apply this approach, this IPC, iterated PC to data without really knowing all that much about the data engineering process, and then from a theoretical point of view that people haven't really considered these a data engineering process as general as ours. This is a paper that is kind of either you say everything or you don't say anything. It is kind of if you open if you open up certain parts of the paper, then it kind of blows open, and so there's an awful lot of notation that you need to go through in order to get to the core and so on, and that especially when it's a diverse audience, then that can lead to more problems than it helps. So I have deliberately tried to cut down on details, trying to focus on the essential stuff. So should it be that you don't really, despite my efforts here, don't follow or don't understand or whatever, then you just stop me and let me know. So this would be a stripped down version of the full paper. Yes, so this is the model. So it's the same as before. So I'm now just going to put a zero superscript on beta, gamma, and f. These are parameters of the model that we are going to estimate. And we, for later notation, it is good to stack this thing. So this is what you see here. So whenever you see a bold-faced y without the t subscript, this indicates that now we have stacked the time observations on y into a vector that is t by 1. So y is t by 1. and this x, capital boldface x, is t by dx, and so on. And the goal here now is, as usual, to infer beta. So we want to estimate this guy, but this shit that is sitting here is in the way. We cannot ignore it. So this is unobserved. The entire component is unobserved. We cannot ignore it because f might correlate it with x. So this means if we ignore it, then we cannot apply least squares, because then there would be this usual omitted variables bias that will lead to bias and inconsistency. So the main concern is how to control for this, or in the stack notation this. So this will come through also in the estimation process. That will the big issue is controlling for f. So we do need to get through some notation. First, we are going to assume that there are G groups of factors. And these groups, they are basically the factors in order of magnitude. And we assume, without loss of generality, that the first group is the one with highest order of magnitude. So again, if you think about f as a trend polynomial, then the first factor is the one with the highest trend power. This is without loss of generality, this grouping, because we don't assume anything about the size of the groups. So a group can contain just one factor, and that is not a problem. And then these sizes of these groups, this is something that we will estimate alongside with the parameters of the model. So we'll get estimates of how many groups there are, and so on, how many factors they contain, and so on. These groups are going to be important later on. So I'm going to, down here, split up f and gamma into groups. So there are G groups. So f not G. This is the factors of the Gth group, and similarly, gamma not G is the loadings of the Gth group. And again, the groups are ordered in order of magnitude. Yeah. Oops. Okay. Assumptions. So this is again. Now you have to, if there's anything, you just shout out. So this is
let me shout out.
Yes, please do.
So what's the point of grouping?
I'll come to it. It's mainly
okay.
It is not. It's mainly for structuring the estimation procedure. It makes it a bit easier to get that part if you do it in this way. I'll come back to it.
Okay, sure. And then the other thing is N and T are here. So what's the asymptotics with respect to both N and T? Yeah.
I'll come back to this. So this is a good question. So there are two indices, capital N, capital T. Capital N, the number of cross sections. Capital T, the number of time periods. So in this panel here, both N and T will be large. And we will, at some point, we'll assume something about the relative rate of expansion of these two indices. But at the moment, I'm not going to say anything about it. It will come. But both are large. So you can think of this as this is a large panel in that both N and T are large. And this is also the case that most papers in the literature are considering.
I have a question on
please.
more kind of motivation of this. So can I think about alternative approach where I would difference regressors and then use the original by method? instead of considering different rates, different magnitudes, how these two would be compared?
Let me. This is a good point. So for the rest of you, I think this is how the question is. Suppose you knew that f was I1 or unit root non-stationary, or that it contained at most a linear trend, then you could kill that by taking first difference of this equation here. Now everything is stationary. Now you apply bias estimator. This is the question, right?
Yes.
Yeah. This you can do, of course, you can do that. Then you lose two things. First, you have to assume that you know the order of integration. So similarly, if you knew that the highest trend polynomial is in f is trend square, then you could take two differences and you run on what's left. But this assumes that you know the highest order of integration or highest order of magnitude of f, which we don't assume here. Plus, if f and potentially also x is integrated, then by taking differences, you lose this high signal that you have, and yet that you can explore, but that you miss out of by taking differences. So in that sense, it's kind of like in the time series literature, if you have co-integration and then your least squares estimator of beta, it's super consistent. If you take difference to kill the trend in x, then you also lose super consistency and you're back to square root of t consistency. And so this is also something that you, if possible, one would like to preserve. But this is good. So this is a possibility for sure.
Yeah, actually, I like this analogy to co-integration stuff, because when I talk to applied people, it's frequently they say, we are okay to lose this efficiency or whatever, because the drawback of using co-integration stuff is that tests are has little power, so it's know really what's going on there. So they prefer just to take differences, and so similar question arises here to me.
Yeah, exactly. No, and as you say, in practice, this is often what people do. But if you have at some point in life made a Monte Carlo, and looking at the loss of efficiency from taking differences, when you do in fact have co-integration, then you know that this is super costly, and so there are good reasons to wanting to preserve that high signal that you have. But that's a good point. Alrighty, so here these are the assumptions. So again, scale down. I'll try to explain what this is. So if we look at the top equation first for the regressors, here we are saying that basically this second moment matrix that we have here, this should converge this thing there. This should be positive definite. The main difference, so if these had they been identity, then this is the usual condition in a stationary model with stationary regressors. The second moment matrix, if you normalize by 1 over the sample size, it converges to a positive definite matrix. This is the usual least squares identifying condition. Here, the regressors can have different order of magnitude, and therefore we need to scale them appropriately, just as you do in time series models with regressors of different order of integration or trend degree. So this is this is not surprising at all. And so then this D is there to account for these different orders of magnitude. And here in our notation, they are represented by kappa. And so each regressor, so there are x kappa. So each regressor could potentially have their own order of magnitude or integration. Yes, I'm just going to point out also that so D is this normalization matrix with respect to T. This is going to pop up later. This guy here will pop up as well. So this is the usual projection matrix. So it's this. So M is the projection error matrix and P is the projection matrix itself. So you can think about, again, if we go back to the case when this D is identity, then if you knew F, then this is the usual least squares condition. Then you would project away from F, and then you would apply least squares to those projection errors that you would get. So this is not really that unexpected. In Yushan's paper, D is identity because he assumes stationary regressors. The factors, they look pretty similarly, and again, this is again not unexpected given the time series literature. Again, the factors are bunched in groups with different order of magnitude. And this order of magnitude is determined by these nus. So there is nu1 through to nu g. And as I said, and as I mentioned before, we are assuming that the first group, is the one with factors that are of highest order of magnitude. So therefore, nu1 is larger than nu2, and so on. So nu g is the group which where the factors have lowest order of integration. And this nu g will pop up later. But the idea is basically the same here. So we require that the second moment matrix of F, after scaling by C to account for this difference in magnitude, this converges to a positive definite matrix. Yeah, here I'm not written it out. Yeah. So these are the main assumptions on the regressors and the factors. We need other assumptions as well. Here's one. So if there's just one group, then we don't need this. But if there are more groups, then we cannot separate groups without assuming that they are orthogonal in a certain sense. And this is also quite common in the literature. And so here, if you take the first condition up here, so if we take the loadings from two groups, G and H, so recall that these big gammas, they contain the stack of all n loadings for group G. These contain so gamma H, all n loadings for group H. So if you take the cross product, this is a sum of n terms. And the assumption here says that this is at most order n to p, where p is smaller than 1. So this rules out the case when these loadings are, for example, constants, unrestricted constants. If they are, then this cross product here would be of order n, which is not permitted by this assumption. So some kind of orthogonality of the loadings, and similarly also for the factors, are needed. Otherwise, we cannot separate the groups of factors and loadings. This is quite common in the literature on grouped heterogeneity. And typically here, this is not enough, but people assume even that this is in fact 0. So complete orthogonality, if you want. So and this is necessary if you have more than one group. Then we need this. The rest, there are other assumptions. We haven't said anything about the assumption on epsilon, so the idiosyncratic error term in the equation for y. This is basically standard conditions, so I'm not bringing it up. So we allow these to be, so epsilon, for example, it could be weakly serially correlated, weakly cross-section dependent, heteroscedastic in both directions, and so on. So the conditions on those are basically the same as in Yushan Bai's paper. The conditions are in the paper, but I'll not spend time going through it here. So I'm just going to stress those things that stand out as different from these other papers. Those are the assumptions. There will be also later on. There will be an assumption, or soon, I think there will be an assumption on the rate of expansion of NNT as well, but for the moment, these are the assumptions. The estimator, it contains 3 steps. So in the first step, we kind of initiate the procedure. Now we, the first step estimator of beta and f is simply the least squares estimator. Minimize sum of square residuals from the model that we have. Subject to, so these are the usual bespoke component conditions on f. And this initial estimator, this is exactly Yushan Bai's estimator. The least squares estimator of f and beta from this model when estimated jointly. Here, there are 2 nuisance parameters, delta and Dmax. These are parameters that the researcher needs to pick. Delta, the choice of delta, is this is arbitrary, so you can put that. So typically, this delta is set to match the order of integration of the factors. So in the existing papers, so if f is stationary, then f prime f over t, you would expect that to converge to a positive definite matrix. So therefore, in stationary environment, typically delta is set to 1. If it's a non-stationary, so if f is a pure unit root process, then delta is typically set to 2, at least in the theoretical analysis of those papers that assumes. But here, since now we're having this general treatment, as a byproduct, we also found out that actually this delta is arbitrary. So it's not necessary to know what it is. So you can put it to 0. So it's something that the researcher needs to choose, but it's arbitrary, as I said. Dmax, this is basically an upper bound on the number of factors that you allow, and this is in the entire literature. So all literature, all the literature that allows for factors in the way that we do here, they have to say something about the maximum number of factors. So as I said before, so in CCE, this Dmax, this is equal to 1 plus dx. So the number of observables, so y plus the x's that you have. But this is a number you need to pick. So that is the initial estimation. Now comes the estimation of the factors. So first, now the initial estimator, because the first group of factors is dominating. So this is the one that is trending the most. Because of this, the f hat that we get from the initial estimation procedure, this will tend to estimate the first group of factors because this is dominating. So we put Dmax So this was the largest number of factors. So we put this to a large number to ensure that we got all the factors. So most likely now Dmax, this is overshooting the number of factors in the first group, D1. So the first order of business now is to shrink the dimension of this f hat, to bring it closer to D1, because we know that f hat is estimating the first group of factors. And so there are various ways of doing that. We do look at the ratio of eigenvalues. So this is basically like a scree plot that you do often in statistics when you do factor analysis. You look at it like this elbow where the explained variation drops off most, and then you set the number of factors accordingly. So this is not strange. An alternative way of doing this would be to apply an information criteria, but here this is going to be complicated by the fact that we don't know the order of integration of the factors. So by taking a ratio like this, the estimator of D1 in this case, it's self-normalizing. So it takes care of this fact that factors may have different order of integration. These lambdas, these are eigenvalues of this second or this covariance matrix here. This is basically what you would have if you took Gaussian bias estimator, you applied it once, and then you wanted to estimate the number of factors, and then you looked at this ratio of eigenvalues. Then you would think now you would be estimating df, so the number of factors, but you are not. So if you just do this once, you are just going to get an estimate of this group of the factors that are of largest order of integration. You don't get the rest. So therefore we need to do this again, but we need to condition on the first group that we have just estimated. So here we are just iterating this now. So basically next step is to estimate the next group of, so the second group of factors. So when we do this, the only thing that we need to do is basically when we take the eigenvalues, take it from this covariance matrix here, where we have conditioned on previously estimated factors. So we estimate the factors that are largest order of integration, we take them out, then we estimate the next group, which is then after netting out the first group, this is the one that has the highest order of magnitude. So we can just iterate this argument that I had before. So we principal components will be estimating the group that is dominating, controlling for the first, the second group is dominating, and then we'll just continue on doing that until we have estimated all groups. And then, so the third step, so first step, initial estimation, second step, iterative estimation of factors, third step, final estimation of beta. So here we take, so beta hat, this is going to be the final estimator. So this is a Gaussian bias estimator plus something that looks like a one Newton-Raphson update or something like that, where you see that there are a bit of there are different terms. You see that the initial estimator is here, and you have beta hat 1. And beta hat 1, so it is here. So it is beta hat, so this is beta hat. So this is the usual least squares estimator, if f is known. And beta hat 1 is this evaluated at f hat. So this is the vector or matrix of all the groups of estimated factors. So you would, I mean, intuitively, you would think that this beta hat 1, that this would be a good estimator of beta itself. Because you estimated f iteratively, like we did in the second step. So now you have estimates of groups of factors in this f hat. So then intuitively, you would think that, well, now if I am to estimate beta, then I just take this formula for the least squares estimator and just plug f hat in. but actually this is not going to work. So if I have time, I'll show you later. So this is dependent on nuisance parameters, so you cannot just do that. So you need to do this correction here. Yeah, and this is the estimation procedure. Some results. 10 minutes. Some results here too. I've scaled away a lot of results.
Joakim.
Yep.
So there was this parameter delta at the I think original or the first stage, the first step. So, and then it doesn't matter how you choose the delta in the initial estimation.
Yep.
Can you
exactly
give some intuition, or yeah, it seems interesting.
There is an intuition, but it's kind of even that intuition is kind of far-fetched. So it's better if you just take my word. It doesn't matter. If you want to, we can discuss it afterwards. But it doesn't matter for the estimation, and actually the estimator is exactly invariant with respect to this parameter.
So that means that initial. Okay, just to clarify what you say right now. So the estimator is invariant, so that you have numerically the same numbers for the initial estimator by trying different deltas.
Exactly. All right. So coming back to this, some results. First, so this lemma. There are a number of lemmas in the paper. And this is one of them. So here, consistency of the common component. So here, the groups and of F. So under the conditions that we put up, then we can estimate the groups consistently. So we can estimate the size of each group. We can also, so here P, you recall P was this projection matrix. This second result, this is a consistency result for the factors. So since both gamma and F, so gamma loadings, F factors, unobserved, we cannot separately identify gamma and F. We can identify the product, so we can estimate the product consistently, but not them individually, because you can always sneak in a matrix R inverse in between, and so you wouldn't know what you would be estimating. But this rotation or scaling by this R, whatever we like to call it, it disappears in this projection, because you have F prime F in inverse, and then F prime again. So whatever positive definite matrix you multiply F with, it cancels out. Think about it as a consistent result for F that accounts for this fact that both factors and loadings are unknown and can be scaled arbitrarily by a positive definite matrix. So factors and group sizes can be estimated consistently. Before we discuss the asymptotic properties of the estimator of beta, we need more assumptions. Here's one. We need to assume something about the rates of n and t. So at this point, so here, this lemma, it just assumes nt both large. That's it, nothing else. But for when studying the properties of beta hat, then now it's necessary to assume something about the rate at which these two indices goes to infinity. And this is kind of standard in the literature. But the cool thing here is that, okay, so look at these. So there are two conditions. So here we take n over t to eta g. So eta g, this was the scaling in terms of t of the group of factors that had the lowest order of integration. So this has the weakest signal, and therefore this is important when kicking out, for those of you that are working with asymptotics, in order to kick out reminder terms, those factors that have least signal would be important. And that's why this eta g enters here. It also enters here. So you see that these two conditions are basically the inverses of one another in some sense. So here you have n in the numerator, t in the denominator. Here's the opposite. So in order to see what these means, so these raw 1 and raw 2, these will be very important on the next slide, because there is going to be a bias in the estimator that depends on both of these. So if we can make both of these 0, then this bias disappears. If we can make 1 0, then that's good, because then there is just one bias term, and so on. If both remain, then problematic. And so if you now try, so if you put eta g to 1, so this is the case where there's just one group, and the factors, all factors are stationary. So this is Euclidean bias case. In this case, then you see from the first condition that n over t, because nu g is 1, n over t should then converge to rho 1, which is exactly equal to the inverse of rho 2. Because if you put in a 1 here, you have t over n. And so here I'm also put this in red. So as Artem said before, we are getting old. So I need to put everything I need to say in red, otherwise I forget about it. So I also put this in red. So you see that this is now this parenthesis here. Doesn't include 0. So rho 1 and rho 2 cannot be 0. So this means that, you know, in terms of this bias that depend on both rho 1 and rho 2, now there are two terms, because rho 1 is equal to the inverse of rho 2, therefore 0 cannot be included. If we put eta g to 2, then this second condition, now you have 1 over n here, which when n is large is going to be 0. So asymptotically, n2 is 0, and the condition n for the first condition is n over t squared, rho 1. So this condition is weaker than this. So n over t to a constant is stronger than n over t squared to a constant. And if we now take this to the limit, we put nu g to infinity. Then you see, looking at the conditions, then both rho 1 and rho 2 go to 0 without any conditions on n and t. So by having factors that have larger order of magnitude, we can relax the condition that we otherwise would need to put on n and t. Plus, we get rid of the bias. So as I said, the bias will depend on rho 1 and rho 2, and it goes away if they are 0. And this is the case here. So formally, it's like this. So this is the theorem. I've not written down everything because it's in the paper and it's kind of messy, as I said. So again, if I write one of these down, then I will have to have pages with notation, and so this just makes it a bit simpler. So again, I've highlighted. So here you see. So this is the question I got before, that by not taking differences, we gain rates of convergence. So it's the usual stationary convergence rate, square root of n and t, and then we have this additional convergence rate that comes from this scaling by the order of magnitude of the x's. So if x is a unit root process, then this d is square root of t, so that the overall rate of convergence is square root of n times t, which is just what you would expect. And this is mixed normal, not normal. It is normal conditional on f. Unconditionally, we don't know what the distribution is, but it doesn't matter, because when making inference, mixed normal is good enough. So given mixed normality, we can do inference just as usual, because the dependence of f cancels out if you do a wall test or a t-test or similar. But here you see the bias. So you see that, so it converges to a mixed normal. So if you look at the estimator itself, this is consistent. So if you divide through by this, obviously it goes to 0. So the estimator is consistent, but there is a miscentering of the asymptotic distribution that depends on these rows. So the rate of expansion of NNT. If both rows are 0, then this bias disappears, and so the asymptotic distribution is centered at 0 as we would expect. But then, so for consistency, this doesn't matter. But for testing hypothesis, this is key, because then we use this distribution here to make inference. So yes, so in general there is a bias here, but in the case when we have f has a high order of integration, then, as we said, then row 1 and row 2 are both 0, and therefore the asymptotic distribution boils down to this simple expression over here at the bottom with a 0 here. It has a well-centered asymptotic distribution in this case. And this is nothing, obviously, the eta g to infinity, obviously this is not true in practice, but n and t equals infinity, this is also not true in practice. So this is, you can view it as an approximation. It just says this, that if you have factors that are heavily trending, then you can ignore this bias that you otherwise have. So Monte Carlo? No, I'm out of, okay. I'm out of time. Yeah, so do you want to see Monte Carlo? I have an application too. I thought.
I see you have 10 minutes, maybe more.
Okay. Let's skip the Monte Carlo. It's just confirming those results that we had anyways. All right. Okay, so now we need to hurry. Okay. House prices. House prices are rising. In Sweden, they are rising really fast now. We have a house. We're super happy about that. So here, this is a Journal of Econometrics paper by Holly Hashem Pesseran, so the Hashem that came up with the CCE and some other guy. And they looked at, so they wanted to test basically whether house prices in the US had been subject to a bubble. And then typically in this literature, there is, you test if prices are co-integrated with what they typically refer to as their fundamentals. So here the fundamental is income. So if this this theory is correct, and prices and income should be co-integrated with co-integrating vector 1 minus 1. So the difference between P and W, this should be stationary, so that prices follow income. If co-integration does not hold, then prices do not follow fundamentals, and therefore this could be indicative of a bubble, that prices are increasing above and beyond income. So Holly and these guys, they argue that So people typically don't find evidence of co-integration, and they argue that that could be due to omitted unobserved heterogeneity or cross-section dependence. What they do is, so this is the most important slide, I think, on this application, is that they apply, in order to see if prices and income are co-integrated, they apply a unit root test to their difference. So, testing for co-integration, assuming that the co-integrating vector is known here. The only issue is that this test that they apply, again, this is from this Hashem guy. This test allows for possibly a unit root common factor. So when you are testing if this difference is stationary, we're basically testing the idiosyncratic variation of this difference. So this common factor, you just take it away and you never get to see it. So it doesn't appear in the test. So the test, so if there's a unit root factor in this difference between P and W, then the test will not detect it, because it's designed to test for a unit root in the idiosyncratic component of whatever variable that you put in. So this means that, and they find that P and W, they are unit root non-stationary, and that the difference, P minus W, this is stationary. So they reject a unit root in this difference. But then again, this could be due to this factor that the test allows, but that you cannot test. It just takes it away. So therefore, as I say in the bottom here, this test is unlikely to detect if these two variables are not co-integrated, and that this is due to a common factor in this difference that the test just takes out before it tests the idiosyncratic component. Did you follow this?
But the question, wouldn't your estimator also take it out?
Yeah, it also takes it out. So I'll come back to this. This is a good point. I'll come back to it. And so here, just to kind of, you can kind of, just as in time series, you can kind of see it just by eyeballing the data. So here, these are, we have state data. So the cross-section dimension are the states in the US, and then we have observed those for a number of time periods. And these are those, so this is prices, this is income at the bottom. And you don't get to see which state is which. Doesn't matter. The only thing that matters is that, so you see that both are, there's a large degree of co-movement among the theories, both here and here. It seems as this common factor interactive effects specification that we have, this seems to be reasonable, let's say. And you also see that, suppose now that you regress P on W. Now there is this cycle that is in P, obviously not captured by W. Just by looking at the data, it would seem, if you now take this P minus W, you take this difference, basically the residual, taking the co-integrating vector as known, then there should be a cyclical component left. That is in P, it's not in W. So basically, this is just the kind of eyeball analysis that you would do in time series if you looked at two variables that were potentially co-integrated. Just by looking at data, you're basically looking at the stochastic trend. The stochastic trend should be the same in the two variables if they are co-integrated. Here, this does not seem to be the case. Moreover, this stochastic trend in P seem to have a strong common component. So it's not stupid to think that there is in fact a common factor that is not taken account of when you just take the difference between the two series. All right. So now we come to the actual implementation. So the idea here is that the approach that we have, this IPC, it doesn't say anything about whether there is co-integration or not. And this, I picture this as a, an advantage that we don't need to know the order of integration of X and F and so on. But obviously for interpretation, it can still be important to know. But here for simplicity, we just don't really discuss this. So here we just want to see whether the evidence is in favor of the results that already exist based on restrictive assumptions. So when we apply the IPC approach, we find that there are three groups of factors and that there is one factor in each group. So recall, these are the sizes of the groups. So this, and we apply three estimators. So the IPC and the original PC estimator of pi. My time is up, but it's just one slide, so I'll just show you. And then we apply fixed effects, the usual estimator. A priori expectations, fixed effects is invalid because we are estimating three factors. Fixed effects can allow at most two, and they have to have this additive specification. PC should not be valid either because the factors, they have different order of magnitude. So there's not just one group, but three groups, which it cannot handle. So as I said before, so if you just apply PC one-off, then you would be estimating only the group with the strongest factor. These are the estimated factors. These are the three estimated factors that then, according to the procedure, have different order of integration. But you see here, the third factor, it basically contained this cycle that was in prices, not in income. So just by eyeballing the data, we could figure out that there would be such a factor left after having taken the difference. And so by looking at these, obviously, these are, so we do it in the paper, but you can just see it. These are not stationary. So this suggests then that if you take the difference between P and W, then this is not going to be stationary either if you account for these factors. And so if we apply, if we look at the actual estimation results of the slope of income, which should be 1 according to theory, then recall co-integration with co-integrating vector y minus 1. Then this is what we get. So the fixed effects estimator is far away from this theoretically predicted value of 1. The PC estimator is very close. And if I test if this is significantly different from 1, then I fail to reject. So 1 is in the confidence interval. But if we now apply the IPC approach, which is more general, then the estimate increases even further. So you can see by increasing level of generality of the estimator, you get an increase in the estimate of theta. So here, this is way above this theoretically predicted value of 1. So the conclusion then is the following. Hall et al. They conclude that basically there is no need to worry, and that there's no evidence of bubbles in these data. But this is not what we find. So we find that since these factors are not stationary, that there is indeed evidence of bubbles in these data, and that prices and income are not co-integrated. And that's it. 4 minutes over. Sorry.
Thank you, Joakim. Very interesting talk. Any questions?
If you're interested, I'll be happy to send a paper. So I was asked earlier by someone for a link to a paper. So we haven't posted it anywhere yet, but the paper is in circulation. So if you want to have a look at it, then just drop me an email and I'll send the paper to you. In the paper, there is also, so as I said, there is a lot of Monte Carlo evidence, and there is also a second application. I didn't take it up here, but there are a lot of stuff in the paper that didn't fit on the slide.
So I guess in the empirical application, if instead of OLS you do other co-integration estimation methods, they will be similar also to one like OLS. Is it correct?
Take it again.
So to estimate the original regression, you can use variety of estimators,
yeah,
like fully modified or I don't know, some variations of those of OLS. Yeah. Are they going to be similar to OLS?
I haven't tried, but my feeling is that they will be similar to these fixed effects. So least squares after demeaning the data. So most likely, if you do dynamic least squares or fully modified least squares or something like this, where you allow for fixed effects, you would most likely get a number that is close to this. I couldn't say for sure, but this is just my feeling.
So, Joakim, if there is this stepwise procedure inside the asymptotic variance, which of course is complex and is in the paper, but can you give me an idea for what the form of that variance would be and whether there's any reflection of the fact that this is a stepwise procedure?
The asymptotic variance of the estimator?
Of betas, yeah.
Yeah. Let's see. So this is yeah. So as you said, I haven't written formulas for B naught and omega out, but they have the usual sandwich form where this B naught. Now I'm just going to move up. It has this form where so it doesn't. Okay, so the estimator that you use in estimating the variance covariance matrix, it does not really reflect this. So once you have the end estimator, then it doesn't really reflect it doesn't need to be corrected for the iterative estimation. So basically this B naught is just this when normalized, where Z is basically the defactored, loading or something like this X's. So you take your X's, you project away the factors, you project away the loadings, and then you basically do what you would do in least squares.
But wouldn't the influence function for gamma hats be part of the expansion for beta hat?
Take that again.
So gamma hats are there,
Yeah.
which featured in Z hats.
Mm.
And so wouldn't they affect the asymptotics of beta hats in the variance? And if they don't, there has to be some.
They do in a way, because you cannot just go with so you cannot just go with mx or even the mean mx, but you do need to compute this. So this is, it is accounted for when you compute z hat. So there is gamma sitting. So omega, so the middle matrix, I don't even recall exactly how the formula for that, but for B naught it's kind of simple. But if you want to, I can send you the paper, and the formula is there.
Yeah, be interesting to see. One other question. So the x's could be co-integrated, but could the x's and the f's be co-integrated? And of course, in your case, they wouldn't be, because you take the projection of x on orthogonal to f's. That means that they wouldn't be linear combinations of f's. But in principle, I guess that's a possibility.
That was a difficult question. Take another one. No. No.
Never mind. It's just and it's almost midnight here, so
no. This, I haven't really thought about that. So this needs to be positive definite. So I don't know if x and f are co-integrated, then it seems as that then this would mean that this would be reduced rank.
Yeah.
So if that is the case, then that is not possible. But it's a good. I'll write this down. I don't think that we discussed this in the paper. At least, well, yeah. Yeah, I'll. That's a good question. I'll look into that. Thanks.
Thank you.
Any other? Then it was actually quite clear. Then I feel that when I made this presentation in my own head, that this is going to be awfully messy and difficult to understand.
That's the reason it was clear, is because there are a lot of red symbols.
Yeah. Now, this is what I felt too. I don't know if I overdid it, but yeah, I needed it.
It's just fine. Thank you.
I'm really kind of happy to see this result when you have co-integration coefficient 2. We never see these things. So do you know any other examples when the coefficients are not 1?
I wouldn't. So at one point in my life, I used to look a lot on these issues of co-integration and so on. So this was just kind of like a something that came with a paper, that when we started to relax these conditions, that then it came into applications that involve co-integration. But from what I recall, typically in this literature, there is a large obviously it's not explicit, but publication bias that unless you find co-integration with with estimates that are close to what you would expect, yeah, you don't see all that many papers having that. But it feels, to me at least, it feels just natural, having seen this, that then the theory that all this relies on, this would, for me at least, just by looking at this, regardless of what estimator of beta is, it cannot hold. These two, yeah, I would be very surprised if these two were co-integrated. And then it kind of, it doesn't matter all that much what beta is. But yeah, from this literature on bubbles and house prices and fundamentals, I'm not too familiar with that. But in other contexts, yeah, all these parity conditions, PPP, Fisher effect, and exchange rate models, and so on. There, I know, is pretty common to that people do report estimates that are close to the theoretically predicted ones, and you don't see a whole lot of papers published that get results that are kind of far away from those values. I don't know if that is, you know, yeah, why that is. Yeah. Then thank you guys for listening. It was, as I said, it was. I was very happy to get the invite. What's so Anton, you are in St. Petersburg?
I'm in Moscow usually.
Okay.
So I work for Academy of National Economy in Moscow and St. Petersburg University in St. Petersburg. So I affiliated with two universities.
Okay.
By the way, we are planning to run the second edition of our conference in St. Petersburg in the summer, and our call for paper will be available soon, so you can submit there.
Then I will be interested. I have never been to St. Petersburg, but I would really like to go. So this seems like a good opportunity then to go.
Make sure you vaccinate with a Sputnik before
yeah, exactly. I actually got my, yeah, so hopefully, so I actually got my third shot the other day only. So hopefully now one should be in the clear on that. Yeah, let's just hope. All right.
Okay, well, thanks a lot.
Thank you very much. Thank you for listening, and I'll be looking forward to this the announcement of the conference.
Okay.
See you.
Thanks. Bye bye.
Bye bye.